Okay, before we get into common ion effect, which is the other important big topic that comes about when we think about acid-base equilibrium, because it really is going to get us into talking about buffering systems, we have to talk a little bit more about the Ka and Kb values, so these equilibrium constants for acids and bases for ions in solutions, so ionic solutions. So we said in the last video that ions can hydrolyze water, meaning that they split it apart and give the solution a different pH. So let's take fluoride, for example. Would fluoride make a solution acidic or basic? So we're really asking, if I have a fluoride ion in solution, so it's in an aqueous solution, what's going to happen? If we think about water as hydrogen hydroxide, which part of the water would fluoride be most interested in? Well, it would be the most interested in my positively charged hydrogen ion. So I'm really asking, would I make hydrogen fluoride or hydrofluoric acid? So again, what I'm really asking is this a strong or weak acid? And hopefully that you know, because you have memorized your strong acids, you know them like the back of your hand, then you know that hydrogen fluoride or hydrofluoric acid is a weak acid. And because it's a weak acid, it will form, so there's no question about it. It does form, no question. It likes to be together. And so when that fluoride ion pulls the hydrogen away from water, thus splitting it apart, what's left over is a hydroxide ion, and that hydroxide ion then makes the solution basic. If I have a basic solution, and I'm thinking about this in equilibrium, because this process is going to be going back and forth, there should be a Kb value that's associated with this particular equilibrium. But if I go to a textbook or if I go to the internet and I look up the Kb value for fluoride, then I find that it's really hard to find Ka and Kb values for ions. So instead of just having a table of these, we can actually figure out an easy way to calculate them. So let's talk about how we do that just kind of quickly. Let's take fluoride again. We know that fluoride comes from hydrofluoric acid. And if we put hydrofluoric acid in water, then because it's an acid, it's going to donate its proton, forming hydronium and that fluoride ion. Now this looks very similar to what we've talked about before, that there's a weak acid, it's in water, it's going to dissociate, but at the same time, because it's weak, then this hydronium and the fluoride are going to react together and reform my hydrofluoric acid and my water, and there's going to be a specific Ka value that's associated with this equilibrium. Now, if we think about the secondary reaction that happens then, so kind of going back to our fluoride, and let's just list it out here below, that if I have that fluoride in my water, and it's in equilibrium, then that's going to give me my hydrofluoric again, and hydroxide. And we said, well, because this is acting like a base, meaning that it's giving hydroxide in solution, we could say that that fluoride has an equilibrium constant that is basic, so Kb value. Now we know that we can, if we have things in common and we're thinking about overall reactions, that we can add together two processes. And we can remove the intermediates from all of this. So if I'm adding this together and I add together all of my reactants and I add together all of my products, then I can remove the things that are in common on both sides. So if I'm removing my intermediates here, let's do a permanent marker. Then I have hydrofluoric on both sides, so I'm going to get rid of that. I have fluoride on both sides, get rid of that. My take-home message from this whole process then is that I have two waters that are in equilibrium with hydronium and hydroxide. Now you should look at that and say, oh, well, it's the autoionization of water, of course. And then you'd say, well, and this is my equilibrium constant. This is that Kw value. So we know when we add together processes that have equilibrium constants associated with them, so if we add together processes in equilibrium, that there's a relationship between these equilibrium constants of the steps along the way and the equilibrium constant for the overall reaction. We know that the first equilibrium constant times the second equilibrium constant times the third if there's multiple steps, and so on, are going to give you the overall. So the steps along the way give you the overall equilibrium constant. So it's a product here. So this is a handy relationship because whereas there isn't a list of Ka and Kb values for ions, there are lists of Ka and Kb values for weak acids and bases. So in this case, if I know that my Ka value is equal to 6.8 times 10 to the negative 4, and I want to find my Kb value, then that's going to be equal to the Kw, which we know is 1.0 times 10 to the negative 14th, and we know that because of the 14-point pH scale, and we know the autoionization of water like the backs of our hands because we've spent some time with it. So again, if we're kind of rearranging and solving, then we have our Kw divided by our Ka, which again is lookupable. Then we plug in our values that we know here, and we're left with a Kb value that is equal to 1.5 times 10 to the negative 11th. All right, so what does that mean? What information does that give us? Well, this Kb value is giving us information about this equilibrium. It's a small value, right? It's a very small value. So if we think about the products, the concentration of products over my reactants, then that means that there's not a lot of this going on, right? I don't have a ton of extra hydroxide that is produced, so it's not going to be super, super basic, but it still is going to produce some. And that is still going to have an impact on this overall system, because now we can't just think about this equilibrium in isolation, right? This isn't the only thing happening. There's other side reactions that are occurring, and we have to factor those in. So what we're going to do moving forward is see how when we have ions that are in here, when we have extra acid, extra base, how that's going to impact these equilibria. So we're going to go back and revisit a little bit of Le Chatelier's principle as well. So keep an eye out for that video. We'll be talking common ion effect next, and I'll talk to you again soon.